Okay, so today we're going to finish up statistics, and then we're going to do very brief AWS, because most of you already knew enough about AWS. So although I ended up not putting the assignment, I moved it back because I forgot to talk about it last week, so couldn't make it do this week. So last class I introduced the beginning of statistics. Today we're going to look at a couple of particular statistics tests, by far the two most commonly used, how you use them, what goes on with them, which are the T-tests and ANOVA. And then I'll briefly talk about a few of the others, Wilcoxon Test and a few others. So last class, I want to make sure we get this because this is a thing lots of people end up getting wrong. So when I talk about T-tests, there are many kinds of T-tests. So built into Excel are the three most common types of T-tests. And those are, and then in addition to the types of T-tests, there is how many sides do I have? So I can talk about a two-tailed T-test or one-tailed T-test. So in a two-tailed T-test, I'm talking about the probability that the answer is not the same. So the whole T-test is like the underlying hypothesis is these two distributions are not the same. And in a two-sided T-test, I'm really saying the hypothesis, I don't know if it's better or worse. So I can be on the upper, I get one mean between the two populations, so the Simpsons versus whoever those guys are. The Simpsons might be higher, they might be lower. Right? I don't know. I'm just testing, are they the same? And that's actually the most appropriate test for most uses because your initial hypothesis may or may not be, I am better. Right? But if I wanted to say the Simpsons were better, then I can have a one-sided test. Right? But I have to be very careful how I want to interpret that test because the first thing I have to check is if the Simpsons are better than Family Guy. There's an F. It's not just names I have these problems with, right? So, if the Simpsons are, if we want to say the Simpsons are better than the Family Guy, what do I first have to know about the mean for the Simpsons? It's got to be better. If that means larger or smaller, that depends on what you mean by better. But so you have to define what is better. And even before I test for statistical significance, I first have to answer the question, is that true? And then I can do a one-sided test. In general, for your thesis, I always recommend you do a two-sided test. You like to see the difference. A 5% error, so if my type 1 error chance is 5%, in a one-sided test, I put all of that error on one side. In the two-sided test, I put it on two sides. So I split. The most common reason to want to use a one-sided test, though, is not because you think one is better than the other. It's because you actually want to test a mean against a known value. So if I have a Likert scale and I'm looking at users and interpretation, and 3 is acceptable, 4 is good, 5 is excellent, and I want to say the user's answer was that this user interface was at least good, right, which is 3, 4, or 5, then I'm going to compare the mean against the value 3. And then I do my statistical test using a one-sided test because I'm not actually using the other data. So for double populations, it's best to use a two-sided t-test. For the other kinds of things where I have a known value, there's not a measurement, then I use a one-sided t-test. And then there's this question of whether or not I'm actually dealing with populations or not. But for lots of computer science, in fact, I would say for most of computer science, when you're not dealing with human subjects, the correct type of t-test is what's called a paired t-test. And in a paired t-test, I'm not actually looking at the two populations as groups to be measured independently. I'm actually looking at every measurement. So if I run something on a data set that's got 100 images, and I look at the average brightness, right? The average brightness computed by these two algorithms might be, that's not right, the average pixel level accuracy, so how well did it do at labeling the individual pieces. If on every image, algorithm A is better than algorithm B, but on some images, both algorithms do really badly, and in another image, everyone does well, then I might actually have a population where I see a lot of variations because everyone's got this variation. And with that much variation, if I have two very close means, I might not be able to tell the difference. But when I look at the difference between the pairs, so if algorithm 1 is always a little better than algorithm 2, then even though there's a large variation, that difference might become very significant because the chances that randomly, if this is a random process, that algorithm 1 always beats algorithm 2 is very small. Randomly, this is switch order a lot. So that consistency goes into it. So a paired t-test. So as I said, all of these are built in Excel. I'll go through some examples of that in a little bit. When we look at the t-tests, right, we then can talk about for interval measurements or parametric stuff, which is the paired t-test, we can talk about what are called independent sample t-test and paired t-test. So the independent sample is the normal one. And I'm not going to go into great detail, but inside the independent samples, t-tests are actually two different variations, which we'll get to in the next slide. Basically answering, do I assume the two populations, the Simpsons and the Family Guy, do they have the same variance, or do they have, which is hemostatic, or do they have two different variances? They're really different distributions. One's broader than the other, and then they're heterostatic. And then there's the paired t-test. So those are the three types of t-tests we'll do. It turns out that if I want to do the non-parametric versions, the Mann-Whitney test, the Wilcoxon test are sort of the paired up ones that show up with that. And in computer science, this paired t-test and the Wilcoxon test are the two that I think you'll see the most often, because we tend to be able to run exactly the same data through two different algorithms. I use these independent samples only when I can't reuse the data. So if I'm measuring network traffic, I can't, and I have to do it live, then I can't replay it, then I might use that. Or if I'm dealing with human subjects providing feedback, then I would have independent samples. So the other reason that you'll see this test a lot is because it's super easy to compute. We're not going to go through all the math. We briefly talked about it last class, but it's literally built into Excel. Right? The base version of Excel comes with this. Every other spreadsheet comes with it. It's a function called Ttest, and basically you have two arrays of numbers, first array, second array. They have to, if you're doing the paired t-test, they have to be exactly the same size because they're paired in order, row 1, row 1, 2, row 3. So they're paired by rows. And if I'm doing heterostatic, then they don't even have to be the same. The tails are either a one-sided or two-sided test, and then a third parameter, which is a paired t-test, a two-sample with equal variance or a two-sample with unequal variance. So this last parameter says what you have to have. If you don't specify anything, it always does a paired t-test because that's the default value. And the default value is, I'm not sure if it's one or two-sided, but I always specify that just so you're very clear. And literally, that's what you have to do. It goes through, does the calculations, and it doesn't actually return the t-value of the t-test. It returns the p-value, which is the likelihood that the t-value you get is due to random chance. The p-value we talked about last class in terms of this statistical significance. So if the p-value returned from your t-test is 0.01, what can you conclude about your test? I guess you're the only one who was here last week. So if the p-value returned from this function is 0.01, what would you conclude about the test of your hypothesis? Okay. So the answer is that's unlikely to happen by chance because it's the probability that the variation you're seeing is due to random chance. So this is 99% likely that it's not random chance, which means you can reject the null hypothesis. Right? So, and by the way, I posted a message, and I already got one feedback from one of the remote students, but statistics is important, the experimental design stuff, and having run into, and I mentioned this last class, having run into a student in this class like 2 years ago who was doing some of their research and clearly didn't remember anything about any statistics or whatever, and when I pushed them about it, they're like, well, we didn't have any assignments, so I didn't really dig into that material. I decided that was a mistake on my part as a teacher, so, well, actually, we're not going to have an assignment. We're going to have a final exam because it's too late to build an assignment, and the exam will be just answering questions like about what is a t-test, what is p-value, some very basic terms, but I don't want people going on through their career saying, well, I didn't have to study it, so I didn't. That's not the way I approached life, but apparently lots of people do, so we'll have a little bit of a final exam. No. They do it if they're CS majors in undergrad, but if you came from a school that didn't have statistics and you're a PhD student, this may be the only thing you ever see. So.
Because I'm going to be like, I forgot most of this from statistics.
Yeah.
Maybe I should take another statistics class.
Well, whether you should take, but you should review some of this. It's really not that hard, right? We don't expect you to derive these things. So anyhow, the t-test is built in Excel. It's really easy to do. And in my view, as a reviewer, I see lots of papers and I see reviews where people get beaten up a little bit. And I'm one of those who writes those reviews as well. But if I have an experiment and I don't do any statistical testing, then my view is nothing in the experiment is significant. Right? And people will say, oh, but the difference is very large. It's like, if the difference is large and the variance is larger, it's still not significant. So you can do it was funny, as my students were like, we don't have room in the paper for it. It's like, it's literally one sentence, half a line, because it doesn't have to be a long sentence, to say, this difference is significant with p equals 0.01 with a two-sided paired t-test, right? It's a sentence, but it makes the difference between you having analyzed, is this result random or not? So I strongly recommend you at least get to the point where you can do this. I have, in my many years, only once seen somebody complain in a CS paper, happens frequently in psych papers, but that this test was not appropriate. If you put in a t-test, and you should not have used a t-test, but a Wilcoxon test, very few people will really beat you up for it. They might, as a reviewer, suggest, no, it might be better to do a Wilcoxon test. But generally, if you're that close to significance, you're probably not super excited anyhow. And the difference between the Wilcoxon test and the t-test will generally be, what's your p-value? So is it 0.0001 or 0.01? There might be some assumptions. So the Wilcoxon test, which is the next one, we're going to do it very quickly. In fact, I'm going to skip over. The slides have more details about how to compute it. But I realize that we probably don't need a little detail, but I want to give just a little bit of feel for what the difference is. So in the t-test, we assumed everything was Gaussian. We assumed it was normal, right? Which, as we talked about last class, makes sense for some variables, because if the variable I'm measuring is sort of difference from the mean, then that variable, difference from the mean, is always Gaussian. That's the central limit theorem. But if I'm measuring raw numbers, they may or may not be. And if the numbers are normal in one space, and I have some other transform, so I take a log, and not normal in that space. So a lot depends on what the space is going to be. So what I recommend the Wilcoxon test is, when you're not sure, it's actually always safer to use the Wilcoxon sign rank test. If it says there's a difference, you've made less assumptions, and now you're much more confident your hypothesis is true. Because to be honest, the results of the t-test say either the result is not random or you violated the assumptions. But it's harder to know if you violated the assumptions. If the data is not Gaussian, then the t-test doesn't apply. The Wilcoxon sign rank test doesn't make that distributional assumption. So it's really the test between paired data when the data is not normal. This is especially important if you're doing anything with ordinal data or survey data. So even though I gave the example of a survey data where we use one-sided test because I'm comparing to the mean, if I'm trying to make a more meaningful comparison other than like, is it at the middle, the difference between somebody saying this is acceptable, good, and excellent, the difference between acceptable and good is not necessarily equal to the difference between good and excellent. Right? Those terms are not numeric values. So when I talk about the average, what does average mean? Right? If I have 2 horribles and 2 excellents, is that okay? Or is that good? Right? So on a 5-point scale, people have some general idea, but they're not necessarily scaled. And anytime you're doing things where you've taken your measurements and you don't know whether or not I should do a log transform or an exponential transform or whatever, then you definitely want to be using a Wilcoxon type sign rank test. So the basic difference for the Wilcoxon sign test is to exclude any differences. So I have a bunch of pairs of numbers. And I'm really going to count how often does the first one win. So anytime the differences are 0, the 2 values are the same, that doesn't matter. Then we're going to put the rest of the differences in sort of ascending order. Is algorithm A beating algorithm B by a large amount? That's the first one. And then I work my way down, and I'm going to ignore their signs. So I'm going to say big differences to small differences in absolute value. And I'm going to sort of assign them the rank. So, and if any differences are equal, we average the rank. So if I have like three times when algorithm 1 won by 3, and then 3 times when algorithm 2 won by 3, all 6 of those numbers become one sort of average number. And we average the rank, so they go in some order. And then we count up the number of positive ranks at the times algorithm 1 won, count up the number of the ranks of the negative ones, right? And if this was truly random, the underlying idea here is that if this was truly random, then those sort of rankings of which one wins would be about the same. If there's a difference, one sum would be much smaller and the other will be much larger, and then there's an underlying statistic that lets us go in and sort of say, okay, how important is that difference? So we look at the smaller num and call that, the smaller sum and call that t, and then we can do a comparison. So again, looking at this, we can obtain the values with critical values by looking at the data of 5%, 2%, 1%, assuming I have enough data, right? And then I can sort of put all those together. So again, you don't have to know how to compute this. I just wanted you to get this basic idea. The whole test of this is how often is algorithm 1 beating algorithm 2, and then how big are those differences? That's where the ranking comes in. So if I were to have these subjects, and here's the sort of hours of sleep, in this case, this is the example, sleep, the treatment, and the baseline, and I can then look at the differences. I can then rank them, so the biggest difference was here, the smallest difference was here, the biggest difference was there. I put them in rank order, and then I add them up. And the smaller one has, the sum of the smaller ones is 50, the sum of the larger one is larger by is 4.5, right? So all of a sudden, right, we have a significance of the 2%. There's a table we looked this up in. It sort of says, okay, this is probably a pretty effective treatment. Right? Now, if I did this for algorithms, it'd be the same kind of thing. I just sort of go through, I rank them all. Now, in practice, you don't do this. You call off to the Whitney, man-Whitney function in Python, right? If you're working in Python. Almost all the statistical libraries have a function to do this. But I like to look at this because it helps you understand when I'm running an experiment. Sometimes I don't even have to go run all the formal statistic tests to know that something's wrong. If I really think my algorithm's better, and I just start looking at like what's the differences between them at a pairwise level, and one algorithm is always winning, this is going to tell you it's significant. If they're jumping back and forth, then they're probably not significant, and I don't have to go through the rest of the process. But although pragmatically, if you're writing code, to just make your code run through, compute the difference, and tell you the p-value is probably the easier way to do experimentation. If you're dealing with human survey data, it's a lot harder. So for human survey data, you often want to do like a small sample. Let's say I collected the first 5 people. One of the possibilities is that something's wrong with my experimental setup, which we mentioned is a potential problem. So if my hypothesis really is that my treatment is better, and I measured the first 5 people here, I'd be, so okay, I could just do the look at this, right? So the treatment's better, treatment's worse, treatment's much better, treatment's much better, treatment's better, right? At this point, it's like, it's probably going to go with my hypothesis, now go run the rest of the data. Right? I don't have to do a formal experiment to know that 4 out of 5 times it was better. Right? It may not be statistically significant with only 5. But if 4 out of 5 are probably winning, it's probably a good thing, go do more experimentation. So those are the 2 primary things for computer science for statistical tests between 2 algorithms, A and B. Ttest, Wilcoxon Test. So the next group, which is a lot more common and a lot more complicated, and which is, I now have to have comparison among multiple groups. And so I have to tell not just pairwise, right? We'll come back to the pairwise stuff in just a little bit, but or maybe it's the next slide. But there's a test we're going to use called ANOVA, which stands for Analysis of Variance, where ANOVA comes from. This is extremely widely used in every field other than computer science, and it is sadly underused in computer science, where people make the mistakes I'm about to describe to you and don't use ANOVA. ANOVA is not a built-in function in Excel, but it is a free add-on in Excel by getting the data analysis pack. So if you just Google ANOVA for Excel, you can get a plugin and it works just fine. It's actually pretty straightforward to do. But there's been this long fight. There's a package widely used in social sciences called SPSS, for which the university currently pays like $6,000 a year for a license. And it pretty much does ANOVA and 3 other 4 others. It's not really a great package. We pay a lot for it. But ANOVA is built into R. It's computable in Python. There's packages for it. It's very easy. So let's talk about first the problem that occurs. So if I let alpha sub c be the probability of an error in a single comparison, right? So the probability of rejecting the null hypothesis. Then the probability of making no error in a single comparison is by definition 1 minus AC, right? That's what we mean, right? So that's my experimentation where I compare 2 things. And I've said, given my model assumptions, if all those assumptions are true, then here's the probability that I've rejected the null hypothesis when I shouldn't. The problem is if I do lots of pairwise comparisons. So if I go back and I have those three groups, right? If I compare Simpsons to Flintstones, Simpsons to Family Guy to Flintstones, right? I now have done three different comparisons. So if I look at the probability of there being no error in M comparisons, because I've made more than one, then the probability of error in the experiment is 1 minus AC to the M power, right? And this raising of it, to the mth power makes it become not, the chance of there being an overall error is very good. So AE quickly becomes large as M increases. We actually saw this error when we talked about the simple jelly bean sort of experiment, right? If I said jelly beans do this and I run with 20 different experiments with different colors of jelly beans, then there's actually a good chance that I will find a comparison because I was testing each one at the 95%. Well, if I have a 5% chance of error, right, and then I do 20 experiments, my accumulative chance of error gets to be much larger. And that's what this is really all about. So the whole point of ANOVA is to reduce this chance of problems. There's another way we'll talk about it in a second. So the one-way ANOVA test is similar to a t-test, except that it can be used to compare means of 3 or more groups, where t-test only lets you do 2. For statistical reasons, it's generally considered illegal to use 2 tests over and over again. We'll talk about how to fix that with some corrections, but it's generally not the right way of doing stuff. But that's why ANOVA is not used in computer science. We tend to just run lots of pairwise comparisons, or take our comparison, take the winner, and like the next closest one, and just do that comparison. And in some ways, that's got some validity, but it's a little tricky, so we'll have to talk about it. We'll talk more about that later. The two-way ANOVA is very useful because it's the only comparison that lets you look at 2 or more groups in response to 2 different independent variables. And this is the other reason why ANOVA is not that common. We have lots of computer science where we change more than one thing at a time. So we can do a two-way ANOVA. The other reason we don't see ANOVA in computer science is like two-way is one particular set. There's 2 independent variables. We have lots of things in computer science where we have 3 and 4 independent variables, in which case I can't even do two-way ANOVA. I have to do something more sophisticated. We'll talk a little about those at the end. So if I come back to sort of the types of analysis and independent samples, so if I have continuous variables and a dichotomous explanation, which is 2 choices, we do the Wilcoxon and Ttest. If I have continuous data and categorical variables, I can do either ANOVA or linear regression, and then we'll talk about linear regression, chi-squares, and stuff in a little bit. These are the ones that are more common for high dimensions. So let's just sort of go through an example. If we have a recent study compare the hypointensity of gray matter structures on MRIs in normal control subjects, benign MS patients, and secondary progressive MS patients, we have this hypothesis that the increased hypodensity is a marker of the disease. So can I build an algorithm that looks for this and then predicts whether or not the person is more likely to be there? And then we can ask, among these 3 groups, we have normal controls, benign MS patients, and progressive MS patients. Is there any difference among these groups? So I have an algorithm that's trying to predict them. I can ask, is there a difference? So what would be our null hypothesis in this example? Again, we want to have a null hypothesis that we're going to then reject. But what's the null hypothesis? So all of this stuff about MS and MRI, none of this really matters, right? What I'm really saying is we have 3 populations, group 1, group 2, and group 3, and some independent variable, in this case some algorithms process, right?
I don't know what hypointensity is, but I guess the color, the strength of the color.
So hypo meaning I'm low, right? So it's not very bright. Right? But so the terms here really don't matter. So this is I have some measurement over 3 groups. What's my default null hypothesis? Right. Well, the null hypothesis is there is no difference, right? So this is pretty much common. And part of this is how you end up designing your experiments, right? You want to say, my experiment says the null hypothesis is there is no difference among this group of algorithms. They're all equivalent. And then if they're all equivalent, then I can test and answer if that's true or not. So the null hypothesis is that all the groups have the same hypointensity on averages. So we have this sort of categorical predictor of a continuous outcome, which is I don't care that the variable of hypointensity is a continuous number, right? My answer is they're all supposed to be about the same. So I could take those 3 groups and I can do pairwise comparisons. And if I were to do that, just to sort of drive this forward, right, I would do 3 comparisons at the 0.05 level. But what happens to the overall alpha? This is what we just went through that equation, right? So the probability that I will incorrectly reject a null hypothesis, and I can look at that so that the probability the failed rejected is 1 minus alpha. If I do this three times, the probability to reject all 3 hypotheses is 0.875, and therefore my probability of incorrectly rejecting the hypothesis is 0.14, right, which is my probability of type 1 error. Right? So just by having 3 choices, I went from a problem that originally sounded like it was testing it at 0.95, and I'm now at like 0.86 probability of being correct, or 0.14 chance of being wrong, right? This is much larger error. Right? If I have 5 algorithms in my table, this number becomes unacceptable. So we have to fix it. So that's where we come back to the ANOVA. So the null hypothesis for ANOVA is that the means of all of them are the same, right? Which is not quite the same as the original null hypothesis. The null hypothesis is there was no difference. Now we're being more precise. The hypothesis is the mean is the same. And importantly, underlying ANOVA, this is the other place that has some limitations, is we're going to assume that the variance is the same as well. So we're really assuming the mean and variance of all 3 distributions are the same. The alternative hypothesis is at least one of the means is different, or that are errors there in terms of the variance, right? We're going to analyze the variance, but the goal is to use the variance to compare the means. And this is a common source of confusion, right? So underlying ANOVA is to look at the variance in the combined distribution versus the individual pieces. We're not actually going to have to do a tremendous amount of tests with the variance. We'll see what happens as we go through this. So as with the t-test, we really have this continuous outcome, but we've now put things together. The underlying assumptions, the underlying distribution of the populations is normal, and the variance of each group is equal, right? Which is what we call homostatic, right? It's the same what we said for the t-test, right? So, Statistic? Yeah, that sounds right, I don't know. Homo something static, right? So, homostatic. But no, there's homostatic. It's also possible, so you should Google it. I might have introduced a few extra random letters, right? So this is I can misspell my name. Words like that I could easily get wrong. That's correct. That's what I thought. So it's like, I do tend to look stuff up when I'm doing slides. So these are really similar to the 2-sample t-test. We make the same kind of assumption. We're just going to have more of them here. So what is it we're looking for here? So if all the groups had the same mean, and since we already know they have the same variance, because we assumed that, right, then I'd get a plot where they'd pretty much all overlay each other. It'd be pretty much the same overlapping distribution. If the populations were different, then there'll be at least one of them that doesn't overlap enough. So we can sort of look at that, and as soon as I do that, the variance of this combined pile of data is much larger than the variance of this kind of data, right? So if one of the distributions is offset, then the variance will be much larger. And that's really what we're going to try and exploit. So we talk about 2 kinds of variance. We can talk about the within group variance and the between group variability, the between group variance. So within the same group, so within the Flintstones, there's one distribution. Within the Family Guy, there's another distribution. And that would be the intra-class variation. And then we can talk about the inter-class variation between the classes. Or within group and between group. So we can basically look at how we're going to combine that data and look at what happens as we look through the data. We can look within a class, what's the variation, and how do we relate that to the differences in the mean? If we have a large between group variance, then we have a large separation here, and that variance becomes larger than the differences between the various means. Right? So the differences in means, the differences in means become larger than the variance. So, and again, you don't have to remember any of these formulas. I just like to derive them a little bit so you get a feel for what we're actually doing. So we're going to look at the observations from the 2 different groups. We can talk about the means from students I and group J. We can compute the mean of group J, and then we compute the grand mean over all the groups. We can put all these together, right? So we can then use these to look at what happens in the variability. So if I look at the difference between a sample and the grand mean, right? Well, I can actually express that as the difference between the value in the grand mean plus the difference between the group's mean. So I basically add and subtract a number. Weird hack. But now I can group them together differently, and I can see that the first one of these terms, where I have one of the group means and the sample value, we call that the group variability. That's within my group. How far am I from my own mean? Plus, how far is my mean from the grand mean? So I can break the difference between me and the grand mean up into really two computations. The difference between me and my mean, and the difference between my mean and the grand mean. That turns out to actually have two potential values. One is back in the time when people did this by hand, right? Variance is like the sum of the squares, the difference. It's a lot more complicated to compute. So I can reduce how often I have to do all of that by just computing the difference between me and my mean and the other mean, and I can sort of represent a bunch of stuff. So this is just the mean. I can actually play a little bit of the same game for the variance, the sum of the squared deviations. So if I look at the sum of the squares of these things, I can again introduce that intermediate term, and I can break it up in a very similar way where I'm looking at the sum of the squares between the group, which we call the group sum of squares, and the between group sum of squares. So within group and between group. And these have these little standard connotations of total sum of squares, SST, within group, SSW, and between group, SSB. So we're going to compare these to sort of look at what's going on. So in the analysis of variance, we can then write these down, right, in terms of the things we just went through, and we can get back to the group mean, and then we can combine that with an estimate of the group variance and come up with this, our estimator MW, where we're looking at, this is sort of counting how many is in group 1 times the sum of squares for group 1, how many is in group 2, the sum of squares for group 2, and so on, right? Divided by this, and the denominator is really just the total number of samples minus the number of groups. So this is an example for just a 3-group problem. But I really, if I have n groups, I have n of these pairs, and I subtract off the number n at the bottom. So I can play a similar game for the between group variability. I can break it down into pieces, and then I can write down it's between square group. I'm not going to go through all the derivations, because you should never do these by hand. You should use a package that will do this. But this lets us get to what's eventually the important part of ANOVA, which is called the F statistics. And the F statistic has a particular known distribution. It's a statistic distribution, which I can estimate. So the value for the F statistic is given by the ratio of those two sum of squares, which is really just the sum of squares divided by the number of items between, the sum of squares within the group divided by the number of items in that group. And that puts it together. So the reason I wanted to cover all these terms is because if I call any standard ANOVA calculator, it'll fill in a table, we call the ANOVA table, and it'll basically help me understand what's going on in my problem. So I'm going to get the overall sum of squares, and it's going to help explain where the data comes from. We'll see an example in just a second, where we're going to talk about the between sum of squares, within sum of squares, the total sum of squares, the different degrees of freedom, the MS value and the F value, and then finally a P value. So just to sort of go through, show you an example of what this might look like, we're going to take some of these healthy subjects with BMS and SPMS, I don't know what those are anymore. I have some means, some standard deviations, and some sample sizes, and now the question is there any difference? Right? So you can think of this as, I have an experiment, I ran it, and I got a mean and standard deviation for 3 different algorithms. It's really the same question. Is there a difference among these algorithms? And so if I look at the data, the intensity, the brightness, this is the same MRI example I had from before, the brightness has a lot of variation, right? So looking at these, I can decide that one algorithm is better than another. But first I want to ask, is there any difference among them? So go back to my ANOVA, my hypothesis is the same, they meet all the characteristics. I put all that together and I get my test statistic F, and it turns out I can look that up and it'll give me a p-value of 0.0062. Which is much less than 0.05, right? Therefore, we can reject the null hypothesis. Even though there's a great spread in this data, it is unlikely these are all the same. So if I put that in, and I call this from Excel, I'm going to get a table that looks like this. the variation between and within, the degrees of freedom, the MS and the F statistic, and the final p-value. And you can sort of look at this, you can sort of see a lot of what's happening is that the between statistics are very small, but the within is much larger. So within the classes, there's a lot of variation that's going to go on that's going to drive this. Just do one more simple example. This one you can actually get the numbers from and type it in. The other one you wouldn't have enough if you want to do this. But so if I were to take this just three groups of numbers, so I have group 1, group 2, and group 3, you'll notice that for doing ANOVA, the groups don't have to be paired. This is the general consensus. So when you're going to put this together, you're going to compute group statistics. So I get counts, I get sums and averages. And if I put all that together and I get my F statistic, right? Again, this is all the calculations. You don't have to know how to do all the calculations. But if I put all those numbers into Excel and I get my Excel ANOVA output, I'm going to get that my p-value is 0.008. And I can look back here and again, I can sort of see, well, what's going on between my within group and between groups. So the degree of freedom is always 1 minus the number of groups. The total count is 1 less than the number of individuals, just like any other situation. The number of data values for a particular within group sample. So that gives us degrees of freedom. And so when we get done all this set of numbers, back to that example, right? Wherever they came from, they are statistically significantly different. Right? All we can do is reject our null hypothesis, which was that they were the same. Now, pragmatically, that's not really great. First, we have the assumption of normality of the data, and we can conclude that one of the means is different, but we don't know which one is different. Okay, so ANOVA is actually often considered just a first step to say, is there a difference? We can do pairwise comparisons to determine what a specific means, and we'll come back to that in just a second. But one word of caution for the ANOVA calculation rate. It is considered bad form to add in a group that you know will definitely be different. So if I took 3 algorithms that are pretty good, and I added one algorithm that's really bad, then I can conclude from ANOVA that they're different, because I intentionally added something that doesn't really belong. In computer science, though, in real experiments, it's pretty easy to sort of say, well, look, I have the normal patients, the patients with MS, the patients with this treatment, and then I have kids under the age of 3. Right? It's like, why would you add that group? And it makes no sense. But when I'm looking at computer science algorithms, it's a lot harder to know. I've got algorithm 1, algorithm 2, and then I have the straw man, which is really like a random algorithm. It's so bad, right? So you shouldn't be including that in the comparison. So it's easy to get ANOVA to say things are different by adding in really bad things, just it's bad form. So our problem is this didn't let us conclude which one wins. This is the other reason it's not as commonly used in computer science, is because the answer is there's a difference, but I can't tell you who the winner is. Most computer scientists want to win, so they want their algorithm to be better. So we have to do the pairwise comparisons to answer that. So this comes back to the way we handle multiple connections with what's called a Bonferré correction. And basically, this allows us to take p-values and multiplies by the number of comparisons. So if I have 3 groups, instead of wanting a p-value of 0.05 or 0.01, I'm going to demand that I have the same level of accuracy with 0.01 divided by 3, and that will give me things. We still assume that the paired tests, equal variance, whatever. So if I come back to that formula we had for making a mistake, if my probability of making a mistake is 0.05, not making mistakes 0.95, if I do 20 tests, which is what we talked about with one of the examples before, right, then my overall probability of making at least one mistake with 20 tests is 0.642. That is, it's more likely that I will make a mistake than I will not make a mistake. I can't just do 20 comparisons and put them together. But I can do the corrections. So if I go back to that example with the MRI and I look at group 1, the control group versus the benign MS, the p-value is 0.002. The control group versus the secondary, right? The p-value is 0.01, and the base versus the secondary is 0.61, right? And now I adjust those p-values by basically just taking them and multiplying them by 3. So I take my 0.002 and I multiply by 3, and now my statistics value for that comparison is 0.06. For this one, it's 0.04, and for this one, it's 1. We clamp it at 1 if it's greater than 1. Right? So now, so in this comparison, are any of these significant? Well, we might actually decide that both of these are significant because after correction at 0.05, both the base group and the secondary group both have a statistically significant difference. So this is probably what I would say is the correct, most common technique in computer science. Most people don't do the correction, but it's how you actually make it correct. So if I take a bunch of algorithms and do a pair t-test, now if I only do the pair t-test between the top 2 algorithms, I'm actually safe because I only did 2 tests. Even though there's other things in my table, I just compared my algorithm to the current state of the art. And I do that with a pair t-test, I'm probably okay. But if I'm going to compare it with 2 or 3 different algorithms, then I would do this Bonferré correction. So basically, we multiply, if I'm going to do a 2-group problem, I multiply by 2. And this comes back to how do we correct our jelly bean problem? So what do I do to correct if I wanted to test each color of jelly bean separately? So what I want to do is I then want to run these tests with basically divide by the number of tests you're going to do. So instead of having a p-value of 0.05, I aim for a p-value of 0.05 divided by 20, which is 0.0025. Hopefully I have enough data to be able to answer that question, but if I can get that value, your probability of making a mistake, your probability of not making a mistake, you're probably not making any mistakes, so then I take this number raised to the 20th power, and it's about 0.9512. So you can get a feel that even at this level, even with lots of comparisons, this Bonferré correction gives you a pretty good estimate of the overall chance of errors being correct. So a couple more terms. So in statistics, we'll often talk about what's called power. So I have my alpha, my type 1 error is the chance of incorrectly rejecting the null hypothesis when it's in fact true. The type 2 error corresponds to failing to reject the null hypothesis when it's false. And these are really 2 different errors, which, as I mentioned last time, they always trade off. If I increase one, I tend to decrease the other. It depends on how I'm doing it, unless I add more samples. So we talk about the power of a test as the probability of rejecting H0 given that it's false. The power is really 1 minus beta. So when people talk about the power of an experiment or the power of a test, they're really saying, what's the chance that I'm going to fail to reject H0 when it's actually false? So I should have said this is my null hypothesis, right, is false. So I should not reject it, but I am rejecting it. So that's our type 2 error. And the power depends on a couple of things. One of them actually depends on the test. And this is where the place where a t-test versus a Wilcoxon test comes up, or a Mann-Whitney test, or any of the other non-parametric tests. In general, a parametric test, like a t-test or ANOVA, has more power as a test than the other techniques. So if we're talking about our hypothesis being described only concerns type 1 error, we really want to understand when things are going to fail for rejecting the hypothesis correctly. Is n? Well, the first parameter for t-test in Excel is actually 2 columns of data. So when you say the first parameter depends on which library you're using, but in most libraries, the first 2 sets of parameters are the 2 sets of data. Right, so when you say parameters, right, so the first things tend to be the data, and whether or not the data is 1 parameter, n, or 2 parameters, n and m, because the 2 groups may or may not be the same size, right? Depends on which test I'm doing. For the pair t-test, there's only 1 size because they're pairs. For the independent t-test, there's 2 parameters, n, how many items in the first group, and m, how many items are in the second group. For the pair t-test, there's only 1 parameter. How many data are paired? How many pairs are there? For the independent t-test, there are 2 parameters. There's 2 lists, one of size m, one of size n. Now in Excel, you never tell it the size. You tell it the array. and it knows how big that array is because it knows the size of the array, right? So same is true in Python. I give it 2 vectors for the t-test. I don't have to tell it how big the vectors are because the vectors are expected to be every item in the vector is meaningful. So it's not like I have an array and I fill it with some data and leave the rest 0. You just make the array the right size.
Those are in my mind like inputs.
Yes, the arrays are inputs.
But parameter is different from it.
I don't, so that depends on how you define the words inputs and parameters. So the
Parametric equation is, for example,
okay, so the parametric equation for the t-test is based on the assumption that it is a normally distributed data, which then results in the differences between the means being a student t-distribution. So the parametric here means I'm assuming a particular form of the data, not like a parameter I'm specifying on the line. There is a question of what's called the degrees of freedom, which shows up in lots of these tests, and is sometimes viewed as a parameter that I can
that's
input.
what I mean.
Okay. So when I go to look up the difference between the two means in the student t distribution table, I look it up based on the parameter, which is the degrees of freedom, which I could then use to look up, which is actually n minus 1 for a student t distribution, where n is the number of samples in a pair. It is the minimum of n and m moon minus 1, I think, for the independent one, but I'm not positive. Okay, so why does power matter? So in machine learning, reducing the type of 1 error, reducing the probability of a type 1 error means reducing the probability of saying there's a difference in the performance of the 2 classifiers when there isn't. Reducing the type 2 error, which is related to our power, reduces the probability of us saying there's no difference in the performance of these 2 classifiers when in fact there is. So power is really answering the question, how likely are we to discard a classifier that we shouldn't? So is my algorithm actually better and I didn't test it? If a test doesn't have enough power, then this is the kind of situation that can arise. So t-tests generally have more power than the Wilcoxon test, which is why I think they still dominate, because I generally want to make my algorithm look good. So if I use a t-test, I will generally have a greater confidence of this separation than if I use the Wilcoxon test. But from a researcher point of view, I would actually be very cautious about that because you don't want to fool yourself into thinking there's a difference when there isn't. So that's when it's better to not assume things about the distribution, which is really what this is doing. So there's another variable that will sometimes show up, which is called the effect size. And this really measures how strong is the relationship between 2 entities. If we consider a particular procedure, we want to know how significant the effect is. We want to know what the size of that effect is. And there are 3 very common measures of effect sizes. The Pearson's correlation ratio, which is when we're doing correlation, we'll talk about. The odds ratio and what's called Cohen's D statistic. Sometimes they drop the word Cohen and they just call it the D value. And it's appropriate in the context of a t-test. It's measures the difference we're going to concentrate on in the next couple of slides. But very simple, the D statistic is the difference between the mean divided by the pool variance. So it's sort of saying, okay, if I normalize the difference between my 2 means and divide by the overall variance, that gives me the D statistic. It's not really exactly it. It's a much more complicated formula, but in all practical purposes, this is a really good estimate, good enough for you to do. And the nice thing about this, again, this is very easy. I'm just looking at the 2 differences in the means divided by their overall pool variance. Very simple to compute. And basically, if this number is big, you have a very large effect. So if D is 0.2, then you're going to have a small effect, but it's probably meaningful. If D is less than 0.1, it's probably not meaningful. If D is 0.5, you have a minimal effect size that's generally noticeable. If D is 0.8, you have a very large effect size. And if it's greater than 1, like, you have an amazing effect size, right? So this just allows you to, again, look at things and sort of say, how confident am I now? Now, underlying this is actually some of the same assumptions, right? So the D statistic is looking at the intravariance, whatever. So the nice thing about this, again, this is trivial to do without doing a whole lot of statistics. I just look at the difference between the variance divided by this pool mean. Then I can sort of say, okay, my result is probably very significant. I will go look at this and do the full statistics later. I think we'll push through the multidimensional stuff and then we'll take a break. So everything we've talked about so far is really a univariate thing. Right? So I have one independent variable and one outcome. Lots of things are a relationship between two variables, which are called bivariate, and between more than two variables is multivariate. Okay? And this is the other place where CS often runs into limitations, where we tend to actually have lots of independent variables. I can measure how much memory I have, how much CPU speed I have, and how much how much data I'm processing, and then I can look at the overall performance. So now I have a three-dimensional plot. It isn't a single variable. So lots of people will then break their problem down into one-dimensional tests. We talked about like the Latin cross kind of designs, but we're now going to talk about the general relationship in higher dimensions. So, and at a certain level, I would say correlation and regression is the most commonly used technique in science, more so than the actual statistical tests. And we'll talk about how we actually use these for making statistical determinations. So just generally, what is correlation and regression? In correlation and regression, the math is actually the same. It's just the interpretation we're going to deal with differently. So in correlation, I'm going to look for a relationship between x and y, or x1 and y1. There's no direction of causation or association implied. So it's really just sort of saying, how do they covary? Changes in one are associated with changes in the other. In regression, our real goal is to predict x from y or y from x. It implies but doesn't actually prove a causation. In fact, in my view, it doesn't really even imply one. You're implying it by saying, I'm going to call this problem regression. Regression itself, the fact that I put it in regression, doesn't make an implication. That was my choice. I said, given y, I want to predict x. Okay? So x is my independent variable. Given x, I want to predict y. Given this, I'm making the assumption that given one, I can predict the other. As soon as they have a correlation, I can do that mathematical operation. I can predict x from y if x and y are correlated. Doesn't mean they're causal. So when we look at the correlation coefficient, which we're going to call R, it's the most common statistic for measurements of the strength of relationship or the association between two variables. For example, I was looking at income and education. I could look at the correlation between them. It goes from -1 to +1. -1 implies when one goes up, the other goes down. Perfect correlation of +1 means when one goes up, the other goes up by exactly the same amount. Right? Or, by exactly a scaled amount. 0 implies there's no association. So as they go up or down, right? So for example, as price and quantity tend to be inversely correlated, some other things are positively correlated. The full name is actually the Pearson product moment correlation coefficient. And the reason that's important is because there's multiple kinds of correlation coefficients. This is a particular one, but it's the most commonly used. So to understand what's going on in looking at it from a visual sort of exploration of your data, if I have perfectly correlation, it means this variable and that variable follow a straight line. Not telling me what the slope of the line is, it just says it's a straight line. A positive correlation means there's a general trend. Right? So the red dots are sort of going up and to the right. A weak correlation, there's a little bit of a line fit between them, but it's very fuzzy. And then negative correlation is the same thing, except they're going down. Right? So now the red dots are going down and to the right. And the perfect negative correlation, they're correlated. So if I were to look at my scatter plot and I see a trend, this is why it's so common, right? If I see a trend, I can fit a line to this, and then I could sort of say between rural per capita income and urban per capita income, there's a correlation of 0.94. So if I look at some country, I can tell the urban and rural incomes are directly correlated. It's not like there's a lot more income in one than the other. Okay, so one of the reasons this is really common is long before we had computers, the formulas for this were actually really easy to compute by hand, dating back into the 1600s. So people could figure out what was going on. So for scientists in lots of fields, they go through how to do all of these. The formulas are really pretty straightforward. And again, you derive them generally in a linear algebra class. So I'm going to look at the sum of the product divided by n minus the product of the averages. divided by the standard deviations. Put all those all together. Again, almost any package you use will compute correlation for you, the Pearson moment correlation coefficients for you. So really, between two variables, it's straightforward. It's just, are they aligned? But the reason it's much more interesting is we can actually do something for regression in higher dimensions, and I can still talk about the correlation. So the correlation in higher dimensions is going to be a multidimensional thing because I have multiple dimensions. But I'm really just sort of saying, how well does all this data fit a line? In 2D, in ND, I'm going to say, how well does it fit a hyperplane? So I'm going to sort of put all the data together. So for multiple regression, I'm now going to put these with two or more independent variables. The simple linear regression basically comes down to predicting one variable from another, and I can think of it as y equals a plus bx plus some epsilon, and I can then fit the regression line. Now, there's a problem with this particular formulation. Anyone notice what might be problematic with this? So this is a classic problem for dealing with lines, right? This is basically one form of a line, right? But this form of the line can't represent lines that look like this. Right? It can't do vertical lines. And it turns out that relationship comes down to a problem we will see in lots of least squares problems. So if I try and predict my error, my residual, which is how far is a point from this line, this formula is going to assume I'm going to predict errors in a vertical sense. So because it's saying y equals whatever. So this is what's called ordinary least squares. It's the standard way of computing regression. And it does okay as long as the line is sort of like this. The errors become really big if the line becomes very tilted, because it's going to measure errors up and down. Again, I'm just going to mention some of the formulas. You don't have to know any of these formulas. But so as I go through the determination of r squared, it's really just the regression sum of squared errors divided by the total sum of squared errors. And you can put all of those numbers together from the calculations we've seen. So the idea here is that I can represent the total errors as the difference of a point from the mean, and then the difference between the mean and the rest of the data. So I get, again, regression or explain sum of squares and the residual sum of squares. So that actually gives me an interpretation of this in terms of how much of the variance with the sum of squares am I explaining and what's left over after I've tried to explain it by the line. And that's because if the data is following a line, there's going to be a difference among all the data points. But the regression is predicting that difference, so I can subtract the two out. We can then talk about what's called the standard error of the estimate, which measures the predictive accuracy. The bigger the standard error, the greater the spread of observations are on the regression line, and thus predictions are less accurate. So the correlation coefficient, r squared, is actually telling me something about the slope of the line and its behavior, and then the standard error is telling me something about how close are the points to the line. And that's one of the two terms we go look through this. So here I'm going to take the sum of the squared residuals divided by the number of observations minus the degree of freedom. So in 2D, in 2D that's 2, in 3D it's 3, and so on. So what's most important, in my view, for what I want you to get out of this lecture is the ability to sort of understand what's going on in your data. So if I have a perfect positive correlation, right, I can tell what the slope is. If you see a data line like this, you don't need a variable. You've completely predicted it. If I have a very tight spread, I have a very strong thing. Here we're looking at something where we have the correlation coefficient is 0.9 and the standard error is 0.3. Here we have something where we have decreased the correlation coefficient and increased the standard error. Right? So the standard error is sort of about the spread. The correlation coefficient is about what is the slope of that line as I'm looking through them. So you can go through all of that. Now, coming back to this for statistical estimation, if I really have an estimate of my data, my null hypothesis can actually be if there's a change for one unit y a change in y, is there a 1 unit change in x, right? And so on. That's what the correlation coefficient would be. So my null hypothesis would often be that there is no relationship between my variables. X and y have no relationship, in which case the null hypothesis would say that beta should be 0. The line should be flat. There should be no correlation. So if we test our regression coefficients and the answer is the slope sufficiently different from 0, then we reject the null hypothesis that there's no relationship. and we can conclude that X has a statistically significant relationship with Y, if it's just correlation, and X has a statistically significant effect on Y if X is a truly independent variable that affects the measurement I get of Y. So again, this is where causality comes in. Effect suggests causality, but that's really how I got my measurements. Once I put them in the formula, it doesn't know which is which. So for statistical tests and simple regression, the underlying data turns out to be from a student t-distribution, similar to making a normal assumption. The basic underlying concept is if I'm looking at the difference of a value from the predicted line, that's actually related to the prediction of a value from its mean, right? Because the line is just a change in the mean, we normalize it. So we can then conduct that on the statistic. It goes through the F statistic, and it turns out to be identical to the t-test for the two-dimensional version. But for the multi-dimensional version, we end up with multiple parameters, which is the slope in each of the different independent variables. When I look at that, I now get what are called partial regression coefficients. And it really says for each change in that variable, I get one change in another variable. So I get the independence relationship between them. I basically get this linear equation that says I can predict the performance as a linear combination of all my other variables. It's now a hyperplane instead of a line, but I go through all of those prediction values, and I can then say, well, if I change my CPU clock frequency by this much, here's the speed performance I would expect. Now, all of this is linear, right? But assuming I have such a simple linear model, I could do that. And it turns out that very similar, I get the entire determination R squared. I go through the same variables. In fact, pretty much the same formulas. But I have to be a little careful. So as I add more dimensions, every time I add a dimension, I'm going to increase R squared. Because the more dimensions you give me, the better I can fit data to a line. If the data is very flat, it's hard to fit to a line. But if I can have a secondary dimension, I can always get a plane to fit better than a line as I go through that. So, we talk about what's called the adjusted R squared instead of the normal R squared. And adjusted R squared is really 1 minus R squared, where I then divide by the number of dimensions divided by the number of degrees of freedom, or divide by n minus the degrees of freedom. So this gives me an adjustment factor to account for the fact that random things will look more correlated in high dimensions. Again, that's a level of detail we probably don't need to go into, but you need to understand that we do want to interpret them with a correction in high dimensions. So as we go into the interpretation, we're really saying if I hold one variable, this is what's going to happen. So, so if we compare these values and talk about the relative importance, I already answered the question. So if I have two variables where the slope of one is 2 and the slope of the second one is 4, is the average effect of x2 twice as big as the effect of x1? And the answer is not in general. So you have to be careful when you try and interpret these. The size of the variable and the coefficients depend on the scale used for the variables, right? So if I have 3 dimensions, 1 in meters and 1 in centimeters, I will generally expect the centimeters to have a larger coefficient because it's multiplied by a larger number already. So, sorry, a smaller coefficient because it's already multiplied by a large number. So we have to be very careful how we deal with multiple dimensions. So regression coefficients are only directly comparable if the units are all the same. So if I make sure all my units are the same, then I can do regression and talk about one being more important than the other. But if I have a problem where one dimension is CPU speed, and another is RAM, those dimensions can never be made consistent. So I can't look at the correlation coefficients and actually sort of say, okay, this variable is more important. Because I can't trade 1 gigahertz of clock cycle for 1 gigabyte of RAM and make any sense out of it. So they're not exchangeable variables. So if we're trying to decide then, how do we decide the relative importance of variables? Well, it turns out we can use some information. We can't use the correlation coefficients directly because they may or not be measured on the same scale. What could we do? What can we do if we don't know that they're all going to be the same units? I can never make them the same units. So we've talked about before, what might we do to normalize? Well, turns out there's two things we can do, but one of them is actually pretty straightforward, right? We're going to use what we call the standardized coefficients, also called beta weights or path coefficients. We're going to tell the number of standard deviation units a change. So in terms of the number of standard deviation units in Y to produce one standard deviation change in X. We also call these Z values. So this is a common trick. Instead of just using raw units, where units don't have a clear meaning, I convert them to mean divided by standard deviation, or value divided by standard deviation, and I normalize every dimension in my data analysis by its standard deviation. And if things were Gaussian, then this puts them all in a proper normalized form. Doesn't work so well if they don't, if they're not Gaussian, but it still works pretty well. So these coefficients measure things if we had every variable in standard form. So one way of doing this, which is actually pretty common in machine learning, is to actually take all your data, and before you do anything else with it, it is to normalize your data. So I'm going to rescale my data so that for every dimension, it has mean 0, variance 1. Okay? A slightly different normalization, still very common, is to make it so that it's mean 0 and min and max are 1. Right, -1 to 1, right? So in the first one, we normalize by the standard deviation. I might still get a value of 5. The first one is more appropriate if I assume my data is actually Gaussian distributed in every variable. The second approach, where I do min-max normalization, is more appropriate if I assume my data is uniformly distributed as a uniform random number, right? Because the mean and variance won't have the same number. Or if I simply want to bound my calculation and I want to assume nothing about the distribution, which for many people is similar to assuming it's uniformly distributed because they don't know anything about it. They're not exactly the same, assuming uniform and nothing, but they're related. So, as I said, the most common thing, though, in the rest of science is to normalize by what we would call whitening the data, divide by the standard deviation. Min-max normalization has just become more common in machine learning. The min-max normalization is easy because I can do it as a single. I go through the data if you find min and max, which I can do very fast, and then I just normalize all the data with that. No squaring or any calculations. So basically, after I do that, I just recompute the normalized form, and this gives us a better way of saying what do each variable mean. So if I now want to test each independent variable, I can look at each of those coefficients and decide, is this variable important? Right? My null hypothesis is this variable doesn't really contribute to the overall prediction, and then I can reject it or not. And again, that comes down to deciding, is the slope for that dimension 0? And I get that by assuming I'm going to use a t-statistic, or I'm going to divide by the standard error. And again, most packages will do these calculations for you. So I put all that through, and I want to test if the variables are similar. It comes out to be like the F-test, but unlike simple regression, which was identical to t-test, in the high-dimensional case, it's not, because each of these variables become more complicated. But it's possible for the F-test to be significant, but for each of the independent dimensions to not be significant. Okay? And that's sort of an interesting subtlety. I could say that each of my variables alone is not significant, but the combination of those variables together is significant, which is why it's not the same as an individual t-test, or at least related to the factor. So this idea of regression is very powerful, but you want to also be very careful to not just look at regression as a simple thing. All 4 of these plots have the same regression characteristics, right? So all of these have the same mean, the standard deviation, the same correlation, and the same best fit line. But these 4 bits of data don't really make the same prediction, right? So this line, right, looks like a pretty good line except for this one outlier. But that one outlier makes this have the same error as this data, right? This doesn't look at all to me like it should have a line fit through it, right? There's something really vertical going on here, and then something else going on. Right? One of those is an error, but what's going on, right? So just looking at statistics doesn't really help you answer the question. You really want to look deeper at your data. I'm a big fan of exploring it a little bit. And then real data turns out to often be much more complex than a simple straight line relationship assumed between regression. So like here's a plot of the duration, how long does Old Faithful erupt for, and how long you have to wait in between them. And if you look at this data, what's the first thing that you see when you look at this data? Yeah, you see two clusters, right? That's the common thing. So this is a very common occurrence in lots of computer science programs where our results tend to be clustered. I can fit a line through it, but in fact, better than fitting a line through it is to say, there's two clusters of data, I should separate them. And then I can have a model that says, here's one part of behavior, here's another part of the behavior. Okay? As soon as we start doing that, we start leaving the ability to do really nice, simple statistics. And then I think I mentioned some of these before. We also want to be very careful of unrelated things seeming related because there's a higher level variable, right? So here is ice cream sales related to drowning. Gives us a nice relationship. Those two are not causal, right? You can eat too much, you cannot. You eat too much, you cannot swim, right? The problem is there's this whole variable of like summertime and whatever, right? So we want to be careful what's going to go on. So regression doesn't prove direction or cause, as I said, and I sort of made that comment. Lots of people will say that regression is a way of testing for causality. In my view, that's completely bogus. Regression is a mathematical tool I use. How I want to interpret it depends on what I do. So if I were to look at that provinces with higher income can afford to spend more on education, so literacy is lower. Higher income suggests less literacy, less illiteracy, sorry, or higher levels of illiteracy and thus the lower levels of illiteracy, the more high income jobs, so less literacy relates to higher income, right? Both of those are exactly the same regression problem with two completely independent hypotheses of causality. And regression will never answer those questions. Right? So if you know variables are correlated, they will always fit a regression model. Right? Regression is in large part about you making the argument, here's what I'm going to do. So regression is a tool to use. Now, it turns out there's some other forms of regression, which I forgot to add slides about. So regression actually has this error model, which I briefly mentioned. I thought I was going to add slides and I forgot. So the error model of standard regression is this, what we call ordinary least squares. And here we assume the errors are all in one direction. If I have a problem where I'm not sure what that slope might be, as the slope gets to be very high, this gets to be very inaccurate. Another approach is to measure what we call normal least squares, where I measure errors perpendicular to the line, where I assume maybe X is the error, not Y. So if I'm measuring certain things, I can be very sure the X direction. I counted how many people walked into the room. That's a variable I have no error in. Right? On the other hand, if I measured my clock frequency, I asked my CPU, the clock frequency can vary in my CPU. So it may actually vary over a window of time by a couple of numbers. And so now I don't know exactly what it was. Then there could be an error in X. And then I don't want to use what's called ordinary least squares. So in lots of systems, there's another technique called normal least squares, which will allow you to get something where you assume there's an error on X and in Y. And then you can sort of run through those. And there's another more powerful tool that's come out in the last 20 years, but more commonly used in computer science, is what we call support vector regression. So regression as a straightforward tool assumes everything is linear. If I don't have linear data, I am forced to linearize it. But then I have to guess, is this an x squared relationship? Is it a y squared? Is it x cubed? Is it exponential? I don't know what it is. Support vector regression allows me to use machine learning tools to get regression data by basically having it simultaneously estimate the functional form and the fit. And that can produce some pretty good results. In the world of psychology and some of the other social sciences, they don't trust the R value you get from support vector regression because it doesn't have the same meaning. You do not fit a whole lot more stuff. Computer scientists, it's sort of still considered okay. From a statistics point of view, there's no justification for it because I've now done a full functional fitting. I get all kinds of stuff. So it's in this sort of weird mix. But that also brings me to the next problem. What happens when there's not enough data? And this turned out to be a really common problem in certain kinds of computational experiments because you simply can't afford to run all the experiments you want. So there are three classical statistical techniques we're going to talk about very quickly. Bootstrap, Jackknife, and Cross-Validation. So Bootstrap is a method for estimating a sampling distribution by resampling with replacement from the original. The Bootstrap procedure allows me to sort of say, okay, I'm going to say I have a bunch of urns. Instead of having lots of urns with lots of balls where I can take them out without replacement, I'm going to say, okay, I'm going to sample, and then I'm going to put them back in, and I'm going to let it sample again. So anytime you see something that says Monte Carlo simulation, or pretty much any use of Monte Carlo in computer science, means they're doing the bootstrapping technique. They are using a randomized algorithm to pretend they have more data than they actually have. So they can then sample at random from these statistics and do some calculations.
Well, like I've seen them use that. I've seen the Monte
Carlo
Carlo simulation
right.
and a bunch of CS papers.
Right. Yeah, and so the reason you use it is, well, I have to be careful. Some people might misuse the term because anytime they do something randomized, there's some people that call it Monte Carlo. But most techniques that use the word Monte Carlo really are doing a Monte Carlo bootstrap sampling. So I take some set of samples. Now I randomly choose some set of parameters. I do something. I can randomly choose another set of parameters and do something. So oddly enough, bootstrapping is a way of solving a problem when I don't have enough data. Randomized sampling can also be used when I have too much data, but not really too much data, but too large a parameter space. So if I'm searching a very large parameter space, I can randomly choose a point and sample it and assume I've done a sampling. But the two are actually very much related. So if I have all the possible samples I want, and I sample without replacement, so I randomly choose a point in space, we actually call that a randomized test, which some people will still call Monte Carlo. If I have a subsample of my data, and I sample without replacement, so I just randomly choose a point, but I never use the same point twice, we'll call that Jackknife. And if I sample with replacement to estimate from the full sample, we call that Bootstrap. So these two, and right now we're just talking about Bootstrap, right? Because we're going to sample with replacement, right? We are going to reuse the same points over and over again. So let's say I have a limited number of observations in my original data set, of, in this case, of various schools. And then instead of pretending this is the only data I have, I'm going to make a whole bunch of copies. So lots of machine learning techniques will do this. They're going to basically say, okay, I'm going to pretend that's my data. I'm going to make a new copy of it, and I'll run an experiment. So as a computer scientist, I can take that same thing, and I can take my data and generate a sample from that original set of data, run an experiment. Now I can do that again, and I can run that experiment many, many times, basically effectively creating a much larger sample set to work with, or sampling multiple times when we're going to do this. So bootstrapping is useful when there's no analytic formula for sampling the original distribution. Traditional forecasting methods like exponential smoothing or whatever really won't work in these situations. In contrast, when the patterns are regular, they may be difficult to recognize. We want to just do this bootstrap sampling. And it can help us with making our sampling assumptions better. So it makes very minimal assumptions regarding the population. It does need that the samples are independent, but after that, I thought it just requires reorderable, but maybe it doesn't for independence. We don't assume normality. We don't assume there's equal variance. It allows for accurate forecasts of intermediate demand. So if I have my samples, and so what I'm really thinking, a sample that is infrequent will show up in my original sample very infrequently, but when I randomly sample, because it's a small fraction, then it becomes a small fraction as it's been amplified. So if the original sample is a good approximation, then the bootstrap sample will become a good set of populations. There are some people that do bootstrap with combinations, and they'll still call it bootstrapping. Formally, it's not a bootstrap, where if I take two samples and I randomly sample a pair and then I combine them, that's not bootstrapping, because it assumes a lot more about the data. They assume I can average two numbers and make them make sense. The bad part about bootstrapping is if the data set is small and it's not representative, then bootstrapping will just amplify the bias. And there's no way from the data to answer that question, because you're actually asking the question, was the original sample biased or not? If it isn't, it's going to amplify. If it's an unbiased sample, it'll sort of work. So there's a whole bunch of techniques to sort of use this. Actually, given the time, because I want to make sure we get through the other things, we're going to skip over the example there. But basically, anytime you have a bunch of data you want to reuse, you can look up bootstrapping, talk to somebody else. But the simple form of it is really, you simply just resample the data multiple times and generate a new data set. There's a whole bunch of variations, Bayesian bootstrapping, where now I make some extra assumptions and I assume I have some priors on how often each category will occur. And then I use that to change the probabilities of which whether to resample. In block bootstrapping and stratified block resampling both of those are similar. I break my data up into blocks, and I either sample each block independently, or in a stratified block resampling process, I now create a strata, so I do different probabilities for each of the blocks in different combinations, which can allow me to sort of say, okay, I did my original population. This stratified block resampling is a common technique used in polling or other survey type instruments, where I might say, I measured my data and I have 36% Republicans, 70%, or 60-some percent Democrats, and 4% independents, because I sampled biasly. But I know that the national sample is actually, I don't know, one-third, one-third, one-third. So in stratified block resampling, I can sort of say, okay, I'm going to make a block of Republicans, a block of Democrats, and a block of independents, and then I'm going to resample so that I can say, now I want one-third, one-third, one-third. So the stratified resampling lets me change the probabilities. It's also commonly used in computer science, where if my original sample was, say, a population of simple data, and then I want to mix it with expert data and sort of look at what's going to go on, I can do the same kind of thing. Related to that is what's called case resampling, which is really where instead of having the populations, there's some variables I measure that lets me say this is the case of a basic user, this is the case of an expert user, and it's like the same, except I now don't have a population estimate, I have how frequently do I see a particular case. Bias-corrected bootstrap is if I've estimated my bias, so I've got way too many Republicans or Democrats in the sample I gave before, I can use that sort of bias recorrection. Stratified block resampling may or may not be doing bias correction. It can be doing other things as well. There's something called a Gaussian process regression bootstrapping, which basically uses a Gaussian process machine learning technique to estimate the frequencies of data, and then uses that to resample them so that if I have a variable that's supposed to be continuous, and I've measured some discrete samples, the Gaussian process lets me fill in all of the other values instead of just resampling the discrete values I measured. And then another thing, resampling residuals look at the errors that are done, again, to fill in gaps. So Jackknife is a variation of bootstrapping, and it's really a method for estimating and removing bias. There's a couple of papers on this. I'm not really sure because it's removing bias based on a set of assumptions of what's going to happen. It really only works well in some cases, depending on what the biases you're going to observe are. It creates systematically dropping out subsets of data one at a time and assessing the results of the variation. So it's actually going to be related to cross-validation, we'll see in a second. So in Jackknife, I basically take all the data and drop out a small block of data and analyze what the performance is. But underlying Jackknife is that effect on it in terms of removing the bias is true if the bias is linearly predicted well, and not at all true if the bias is exponentially predicted well, because there's an impact of what that's going to do. So Jackknife is less general. It explores the samples. It yields the same results each time, so it's not a randomized technique. It's just a way of improving the estimates. Bootstrap yields slightly different results when repeated with the same data because you have this randomized sampling. There's no theoretical bounds on what's going to happen, so it makes some interesting assumptions, but it's a good way of running your experiments to try and get statistics. So by far the most common thing people will do with Bootstrap is somebody will say, you have a conclusion, but you have no statistics on it. So if I have only one data set, and I want to compare my algorithm to somebody else's algorithm, I can't do statistics. I can't say mine is statistically better. But what I can do is I can take my original set of data, and I can randomly sample from it, and now I can say, okay, instead of having here's a network trace, here is 1,000 network traces. Each one is a random perturbation of the original network trace where I drop out some of the data, and I leave the rest of it there. And now I can run my algorithm 1,000 times, and for the 1,000 times I can run both algorithms and say, is algorithm 1 better than algorithm 2? Is algorithm 1 better than algorithm 2? And maybe reach some statistical conclusion based on that. So it's an easy way to take what sounds like I can't do statistics and turn it into a problem where I can do statistics. And that's one of the places it can be useful. A related technique is what we call cross-validation. And in this case, we're going to partition the data into subsamples such that I can do the analysis on a single subsample or some bit of data and then test on another. And the nice thing about this is they're sort of retained in some order. So if I need timing results, I can still keep all those timing results together. So if I reorder data, and I'm talking about network traffic, it can really be like if the reply is seen before the request. That can break all kinds of algorithms. It's not very realistic. So I can't really just do randomized sampling like it would bootstrapping. So in cross-validation, I break my data up. In this case, I have like groups I use for training and testing. It's really common in machine learning to do this because in machine learning, I want to separate training and testing. So I can train on one part of the data. So in this case, let's say I unfold one, I'm going to train on all the blue and then estimate on the green. Then I'm going to do it another time, I'm going to train on all the blue and estimate on the green. And so my tests, in this case, I get 5 independent tests. The data used for testing was never used during training, and no sample was used more than once for testing, although it was used multiple times for training. So this gives me a nice technique that I can sort of use. Within cross-validation, we actually have this range of parameters for two-fold cross-validation. I break my data into train and test, and train and test, which is breaking the two. The most aggressive form is what's called leave one out cross-validation. I train on all my data but one sample, and then I predict that one sample. And everywhere in between, you can have some other variants of things. So in like scikit-learn, there's a 10-fold cross-validation, 5-fold. You just tell it how many folds you want, and it will do that. As I increase, so if I start with one set of data, I have a very large bias, and I really can't even estimate variance. If I do k-fold cross-validation, I get a medium balance between the bias and a lot of variance. And if I go to leave one out cross-validation, I have reduced my bias in the formal statistical sense, but I've greatly increased the variance because on each of those outcome tests, I actually can't compute much. So if I'm doing machine learning, I can't talk about accuracy. I'm either right or I'm wrong. I made the right prediction or I didn't need the right prediction. So I get no averaging, which increases the overall variance because the outputs are just now zeros and ones. So if I want to compare Bootstrap and cross-validation, although the way I described it sounds like a resampling technique, it's not a resampling technique because every test sample is used exactly once. Bootstrapping, I can reuse them lots of times. Cross-validation generally does require a medium-large amount of data, so it's not as useful for very small data problems, but it's extremely useful in data mining or artificial intelligence or any experimental paradigm where I want to have training and testing. So, but out-of-sample bootstrapping is a commonly used technique in sort of looking at what's going to go on. So if I look at, say, there's 10 sample cross-validation versus out-of-sample bootstrapping, so assume that I have 100 modules and a 5% detection defect ratio. Chances are really good if I do 10-fold cross-validation that I will get a fold that will never have any defects. Whereas if I do sample bootstrapping, it's most likely that every time I do training and testing, I will see those defects. And that's either good or bad. Because if the 5% is my labeling error in data, out-of-sample bootstrapping will make sure that almost every test will see those errors. Cross-validation, it's less likely that they will see it because you don't reuse those labels every time. So there's a nice trade-off in there. So at this point, we'll go ahead and take a 5-minute break, and we'll come back and we're going to talk about AWS. So come back by 3:10.
Sorry, I'm laughing at the fact that
Oh, yeah.
You incorrectly believe your research is not dull.
Yeah.
No conclusions can be made. Good luck, graduating.
This is the dull hypothesis, not the null hypothesis. I thought you might actually like the F's. Upper right. You have to pronounce it properly, then it makes it funnier.
F? Oh
feedback from you.
Yes, apparently no one has. Somehow, the way I put it up, I thought it was there, but
I thought maybe like it was part of the Turnitin thing.
That's why I could not complete because I was in the competition.
yeah. So I will probably just have to mail them out by hand. So I thought by doing what I did, it was going to upload in the system properly, but apparently not. So